Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and this is the conclusion of the lecture entitled Solving Systems of Differential Equations. So this was what you were working on when we paused last time. I hope you finished it, but if not, you have a chance to do it now. You know what to do. Let's see how you did. So here's the system again. Now, the alert reader may observe that since y prime is absent from the first equation, we could use the latter to express y in terms of x and x prime and substitute into the second equation to derive an uncoupled equation containing only x and its derivatives. This won't always work, but it'll work here, and in fact we're going to call that method 2 in just a minute. Okay, so to utilize the elimination method, we first should write this using operator notation. So we reorganize this, getting things in the form of an operator of x and an operator of y, operator of x, operator of y, underneath one another, and this is the right-hand side. So what we're going to do then is we can eliminate the x from this, and we would do that by adding 4 times the first equation to d minus 3 applied to the second. And you see this will be 4d minus 3, and that'll be minus 4d minus 3. And so when we add them, the x's will drop out, and I will get 16 plus, and here are the two operators being multiplied together. Again, they factor and they multiply because we have constant coefficients. Those are operating on y, and that's equal to, and this is on the other side because what I do to one side I have to do to the other. So I am adding 4 times the first equation to d minus 3 times the second. And when I finish that, what I'm going to get is 4 plus 10 minus 30t. And so now I can simplify this expression, and that's going to be this operating on y is 14 minus 30t. Now this is an equation we know how to solve well. We find the homogeneous equation, and then we find a particular solution, and we can annihilate this or something. But this is what we end up with, is that y of t is equal to c1 e to the minus 5t plus c2 e to the t plus 6t plus 2. Now we have two ways to go. One thing we could do is return to the system that we initially had and now just eliminate y. And if we did, we'd find this differential equation for x, and this would be the other side after I do those operations, which are multiplying the first equation by d plus 7, that's really an operator, and the second equation by minus 4, and adding them, and you get this. Now this equation also can be solved. You would use annihilators for this side, and you'd get the homogeneous equation. And so here you would get x of t is equal to k1 e to the minus 5t plus k2 e to the t plus, and this is the particular solution, 8t plus 5. Now these k1 and k2 are arbitrary, but they're not necessarily c1 and c2. But the way we can get those consolidated, and we know that there only should be 2 arbitrary constants, since you got 2 first order equations. So what we're going to do is we're going to substitute what we found for x of t and y of t into one of the equations, and let's just use the first equation. And if we do that and do the algebra, we get this. And when we simplify collecting like terms, we have this. But e to the minus 5t and e to the t are linearly independent. That means that these constants has to be 0. And so that means that k1 is equal to c1 over 2, and k2 is equal to 2c1. And so then we write the solutions in terms of c1 and c2. And that is the general solution. Method 2 is simpler. We just observe that once we know what y is, we can obtain an equation for x in terms of y and y prime, and we can solve, and we get this, and we can substitute what we found for y of t in there, and this is the answer that we get for x, which matches up with what we would get the other way. Now, the above procedure works more generally, for any two equations and two unknowns with constant coefficients, and it have to be constant coefficients or this will not work, regardless of the order of the equations. So if we let L, 1, 2, 3, and 4 denote the linear differential operators with constant coefficients, these are polynomials in D, then you work to get the x's under the x's and the y's under the y's and the, I'm not going to call them constants, but non-x and non-y on the other side. And then what we can do is we can solve these the way we did. And here they're doing something that almost looks like determinants, and in fact that is what will happen. So what you will do is you'll solve this for x and y and obtain the general solution. Now I should say that your book spends a little bit of time talking about using determinants in quotes to solve this, because what you do have is that for the problem that we just worked, this is the matrix that's being times the vector xy that will give you 1 n 10t. And so what you can do is do something like Kramer's rule. We can take the right-hand side column and we can put that where the x is. The x is the first column here, and have the rest of it be the same. And then I can do like a determinant here, this one operating on this one minus this one operating on that one, and have that operating on x, and then do the same thing for y, and we've effectively decoupled these. You don't have to use this process, you can use the other, but I wanted to show you what they're talking about. And again, it really comes from just solving simultaneous equations. Here's a problem for you. I want you to find, please, a general solution for this. It's second order, but that doesn't matter. You know what to do. Let's see how you did. Okay, here's the problem restated. And so we first get it in the form that we spoke of. So we organize it. We have the x's under the x's and the y's under the y's. Those are differential operators, and this is this side. So we're going to eliminate y, which means we're going to have x. And notice that this x is really the determinant here. It is this operator times that one minus this operator times that one on x is equal to, and here, since I'm solving for x, I will have minus 1 and t squared, and then I will have d plus 1 and d. And again, these commute, so when I do that, this is what I get on this side. So that reduces to this for x when I do all of those calculations, and this is an equation that we know how to solve. It's a third order differential equation and is non-homogeneous. So we'd expect that since it's third order, there'll be 3 arbitrary constants in the solution, but we can also find the particular solution. And that's what we did. Our auxiliary polynomial characteristic equation is r minus 1 whole squared, r plus 1, and so that says these are the roots. So the general homogeneous solution for x will be a linear combination of e to the t, e to the t, and e to the minus t. I guess that's a good review for the final. So to find a particular solution, we can annihilate this other side, and we find out the particular solution is minus x squared, not x, minus t squared minus 4t minus 6, and we add those two together and we know what x is now. To find y, we could take the shortcut, and we could subtract the second equation from the first and find out that this is true. So then we can say y is equal to, I just put these on the other side, do the calculation, and I take the value that we found for x and substitute it in, and I find out what y of t is. Here's the last one. You want to find a general equation. This is 3 equations and 3 unknowns. They're all first order though. You know what to do. Let's see how you did. Okay, again, we put it in operator notation, so the x's are under the x's, the y's come next, and the z's come next. Now we can eliminate z from the first 2 equations just by adding them, and from the last 2 you have to do some algebra here, multiplying by 5 and so on and so forth, but you can eliminate it from that as well. You could solve for z here and substitute that in as well. That might actually be the easiest way. And so you end up with this. The x's are over the x's, then the y's are over the y's, so we're going to solve for those, and then we will back substitute to find out what z is into perhaps the first equation. And so when we eliminate x from that 2 by 2 system, you found out that this operating on y is 0, so there's my general solution. It's a linear combination of e to the 3t, e to the 2t, and e to the t. And now what we can do is we can add the two equations above to get an expression for x in terms of y and its derivative. We find that x is equal to this operating on y, which is this, and then we can substitute what we found for y in there, and we know what x is. So x is this, and we can use the second equation to solve for z of t, and z of t is this, and we know what x and y are, so we know what the derivative of y is, and we can substitute in and we get this. And so we found for y, x, and z. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.